So now let's move on to the union find data structure, aka the disjoint sets data structure. And I personally think that this is an underrated data structure. It doesn't really come up super often, but when it does, I kind of enjoy coding it up. Now, it's technically a tree data structure, but it's mostly applied to generic graphs, so it can get kind of complicated, but the implementation is surprisingly easier than you would think. Suppose we had a generic graph that looked kind of like this. Maybe it had directed edges, maybe, this is what it looks like. So even though it's a single graph, we actually have two disjoint sets because the entire graph is not connected. We're used to dealing with connected graphs like trees where every node is connected. We don't have usually graphs where we have two separate entities of the graph, but that's the case here. That's the strength of the union find data structure. It can deal with disjoint sets, where we could have one or more connected components. This would be considered a connected component of the entire graph because all of these nodes are connected. This would also be a connected component, but the entire graph itself is not connected. So if we were given a graph like this, the strength of the union find data structure would be to count the number of connected components in this case. It can also be used for cycle detection. Suppose we had a graph like this. Union find would be able to determine that this graph does not have any cycles. But if we add an edge like this one, union find would be able to tell us that this graph indeed does have a cycle. Now you might be wondering, can't these operations also be satisfied using just a generic DFS algorithm? And usually that is the case. That's why union find is pretty rare to see. Usually DFS can accomplish the same thing in the same time complexity, but sometimes union find is more efficient and sometimes union find is required. So now let's get into the implementation of the data structure. Suppose we're given a list of edges like these, and we want to determine if this graph has a cycle or not. Let's say we're also given the total number of nodes, which is 4 in this case, so we have 4 nodes here. And these are the edges of that graph. Let's say each edge is directed, so 1, 2 basically means 1 points to 2. Let's say in this case, each edge is undirected, so 1, 2 basically means 1 and 2 point at each other. So how could we use union find to solve this problem? Well, first of all, union find is a forest of trees. Forest of trees basically means we have a bunch of trees. The way we initialize this, essentially we have a tree for every single disjoint set. Now initially we assume that all 4 of our nodes are disjoint sets. We don't know any information about these nodes, we just know that we have 4 of them. But now we're going to start going through the edges and connecting these guys together. Now for each node, we don't store a lot of information. We just store what is the parent of that node. Initially, all of these nodes don't have a parent. They're just a single node. But an easier way to do that, especially in terms of code, is just to say that the node itself is its own parent. That's the way I like to implement it, at least. But you can see it both ways. Sometimes people will say it doesn't have a parent. I like to say every node is just initialized to its own parent. And at this point, it gets pretty straightforward, actually. We have an edge 1, 2. What do you think we're going to do among these? Well, we had 4 separate graphs. Now we know that 1 and 2 are connected to each other, so we should connect these 2 nodes. So essentially what we do is we take one of the nodes and set it as the parent of the other node. So in this case, I'm going to say 2 is going to be a child of 1. So now 2 has a parent, which is now 1. It was arbitrary how we did this. We could have also taken 1 and added it as a child of 2. It doesn't really matter in this case, but it will matter in some cases, but we'll get to that in a bit. We went through the first node, now let's go through the second node. And actually, to illustrate things a little bit better, I'm going to do this edge first. So actually, let's focus on this edge first. So 2, 4, we want to union 2 and 4 together. So what should we do? Well, we could arbitrarily take one and set it to be the child of the other. We could take this 4 and set it to be a child of 2. Or maybe we could even take 2 and set it to be a child of 4. But 2 already has a parent, so we're running into a problem. We can't arbitrarily pick in this case. The best way to get around this problem is, instead of unioning the two nodes themselves, how about we go from that node all the way up to its parent and then eventually to the root node of, this tree. This is a tree at this point. And we go to the root, which in this case is just one. But, maybe there were multiple chains and there were multiple nodes up ahead. We would keep going until we got to the root. And then we would take the roots of these two trees and then union them together. Now, in this case, we sort of have a choice because they're not symmetrical in this case. It's not arbitrary which one we pick. They're not the same size as what I'm getting at. So what do you think would be better, to take this tree and add it as a child of this, which would look something like this? Or should we instead take 4 and add it as a child of 1? Well, this one definitely looks a little bit more balanced, but why is being balanced important? Well, what I just talked about. When we are trying to union two nodes together, in this case 2 and 4, the first thing we want to do for these two nodes is find the parent of these two nodes. Or rather, not the parent, the root of these two nodes. So for 2, the root is 1. For 4, the root is itself. And then after we find the parents, we want to then union these two disjoint sets together so that they form a single disjoint set, But we know we might continuously run the find operation on nodes. So if we have a balanced tree, then the find operation is going to be more efficient than, if we just take this and insert it as a child here. At that point, we have a linked list. That's not really efficient to traverse. Imagine we have to find the root of this child, then we have to go all the way up the chain. Whereas if we take this 4 and, move it to be a child of 1, this is a bit more balanced. We don't have to go up, an entire chain. For 2, we just have to go up 1 step. For 4, we just have to go up 1 step to find its root. This operation that we talked about is called union by rank, which just means height. So we take the height of the trees that we're unioning and take that into consideration. We could do it arbitrarily if we wanted to, but it's more efficient when we union by height. We saw that this tree had a smaller height than this tree, so we took the smaller tree and then added it as a child of the larger tree. And even when we connected them, we connected it straight to the root because that also makes it more efficient to find the root. We could have taken this 4 and, connected it over here, but, why would we do that? So now we've processed this edge over here. And by the way, based on these two edges, 1 and 2 are connected and 2 and 4 are connected, we would have a graph that looks something like this, wouldn't we? Where 2 is connected to 1 and 2 is connected to 4. But with our union find, we ended up with a tree that looks like this. 2 is connected to 1 and 4 is connected to 1. Well, that's kind of the point. Union find doesn't necessarily accurately represent the graph. It's about being able to detect cycles and about being able to count the number of connected components. So now let's go through the last edge for 1. That means we have to first find the parent of 4. So we would start at 4, go to its parent and keep, going up the chain until we can't go any higher. 1 is the parent of 4. 1 is the root of 4. And for 1, we also got to find the root of it. Of course, it's itself. So now we looked for the roots of both of these and they're the same. What does that mean? Well, that of course means that these two nodes, 1 and 4, are part of the same connected component. That means that we can't union these. They're already a part of the same set. But we could return some value to indicate we were not successfully able to union. We could return false, for example. Basically, that would indicate that these are already connected. And in the context of this problem, that would indicate that this graph has a cycle because we're connecting two nodes that were already connected. That's at least assuming that all edges here were unique. And in this case, they were unique. That means we must have a cycle. Let's draw what this graph would look like to confirm. We have a 1, we have a 2, and we have a 4. 1 and 2 are connected, 4 and 1 are connected, and 2 and 4 are also connected. I mean, we do also have a 3, but it's not connected to anybody. So this is our graph, and our graph indeed does have a cycle. At least one of the components has a cycle. So now let's move on to the code. It's surprisingly not super difficult, but there are some gotchas, and there are a couple things that we didn't talk about in the drawing just yet. So we have our union find class. The constructor would usually take one parameter, usually telling us the size of our set. N in this case would be the number of nodes of our graph. And we know that for every single node, we want to keep track of what its parent is. I think the easiest way to do that is with a hash map. You can also do it with an array, especially if you're given some values, in between a range of 1 through 4, for example, that could be handled with an array. But I like to do it with a hash map. It's more generic. It works pretty much the exact same anyway. Now, for every single tree, we also want to keep track of its rank. And by rank, we mean height, because we want the height of our trees to be as small as possible. That makes our find operation more efficient. Now, when we have a tree like this, every one of these has a rank. So the height, aka the rank of this guy is 1, the rank of this guy is 1, the rank of this guy is 2. But of course the ranks of these don't really matter anymore. They're irrelevant at this point because we're never going to be unioning these guys anymore. Anytime we want to union 2 with somebody else, like for example 3, we're going to end up going from 2 up to its parent. That's where the find operation comes in. Given some node, we want to find its parent. We want to do that so that we can perform the union operation. How do we find the parent? And by parent, we usually mean the root parent. So P in this case is going to be the parent of N. And by the way, we initialize the parent as itself in the constructor, and we initialize the rank of everybody to 0. That's sort of a default value. We could also have done 1, it depends. Do you count the height of a single node to be 0 or 1? It doesn't really matter as long as you're consistent, because it's all about comparing the height of one node to another. The height of this would be 1, the height of this would be 0, so of course this one would have a larger height. So to find the root parent of 4, we would, go to its parent first of all, so we'd have a pointer to its parent. We could do that using our hash map of parents, and then we would essentially keep traversing up while P is not equal to its parent. So we know that's how we're kind of setting it. We're initializing every node to have its own parent. So that's how we know we can stop going up the tree. So we'd start at 4, we'd go to 1, we'd see that 1 is its own parent, so we can't really go any higher. At that point, we would stop. We would return P at that point. Now, this one line of code might be a little bit confusing. Basically, what we're doing here is path compression. It's an optimization that I didn't talk about yet, but suppose we had another node down here like 5. It's pointing at 4. Let's say we run the find function on 5. We go to 5, we go to 4, then we go to 1. This is its root parent, and then we would return that. Now, simultaneously, as we're going up the chain, we can also shorten it. We can also shorten this chain, and it won't affect the time complexity of our find function. So why shouldn't we do it? It's an optimization that will help us if we ever run find on 5 ever again. 5's parent is 4, but what we're essentially saying is we're going to set the parent of 5. Instead of being 4, we're going to set it to its grandparent because that will shorten the chain. So essentially we remove this and now have a direct link from 5 to its grandparent. And we keep doing that as we traverse the chain. This doesn't make the find operation more efficient as we do it the first time, but if we ever run find on 5 again, it will be more efficient. And since it's just one line of code, it's a good thing to do, but it's not always required in union find. Now, finally, we can move on to the union function. Given 2 nodes in this case, N1, N2, for example, 2 and 4, we want to union them together to form a single set. So what we should do is find the root parent of N1 and the root parent of N2, and then union them together. But in this case, both of them have the same root parent. So if that were the case, we wouldn't do anything. There's nothing to perform. We can't perform a union, so we should return false. False is to indicate that the union was not successful, that these are already a part of the same set. But if that wasn't the case, for example, we're trying to union 4 and 3 together, we would of course get their root parents, 1 and 3 is its own parent, and then we would union them together. Now, the most easy thing we could do is just get rid of all this code, all this, and just have a single line of code like this one where we arbitrarily pick, for one of these nodes, we want the other one to be its parent. So, maybe we say 1 is going to be the parent of 3. So maybe we'd say that this tree is going to be the child of 3. And then we'd get rid of this and we'd get something that looks like this. That's if we did it arbitrarily, and that wouldn't always be efficient. So what we try to do is union by rank, aka union by height. Which one of these guys has a smaller height? Well, the height of this is, let's say 0, and the height of this is 1. So this one has a smaller height. Therefore, this one should be a child of this guy. And that's what these if statements are doing. It's saying if the rank, aka the height of P1 is larger, then P1 should be the parent of P2. If P2 is larger, then P2 should be the parent of P1. So in this case, we would set 3 to be a child of 1. Now, if those are the case, basically if the heights are unequal, in this case, this had a larger height than the other one, doing a union operation is not going to affect the height, because if this one had a smaller height anyway, and we're directly adding it to the root, the height of this is not going to change. It's still 1, as you can see. But if we ever did an operation where we had unequal heights, equal heights, for example, let's say these two were not childs of 1, both of these have a height of 0, let's say, and that's going to be the else case where the heights are equal. Then we would arbitrarily pick, let's say this one is going to be the parent of 3, so we'd take 3 and add it to be a child of 1. At that point, we would have to increase the height. But we only have to increase the height by 1 because both of these heights were equal. They were 0 in this case, but I'm going to use a value like n because it's a variable. The height of this tree was n, the height of this tree was also n. But now this tree is a child of this guy, so we added a bit of distance. We added this much distance. We added an edge of 1. So now the new height of this is going to be n plus 1. Right, that makes up for this distance, and then, this tree has a height of n, which in this case is 0, but it could have been bigger. But that's the main idea. Now, the important thing to know about union find is, of course, the time complexity. Union is a pretty straightforward operation, actually. Like this combination, because we already have the parents at this point, we're essentially just connecting, two nodes together. That is a constant time operation. What's not constant, though, is what we have to do before. We have to find the root parents of two nodes. So the bottleneck is coming from the find function. Now, in the naive case, where we don't implement path compression at all, and we don't implement union by rank, then the find function would be linear time, because we might end up with trees that are just connected as if they were a linked list. That would not be very efficient. Those are imbalanced trees, and then traversing up them would be a linear time operation. Now we can cut this to log n by just doing one of the two operations. We can either implement path compression, which is just a single line of code. That will take our find function, at least on average, and change it from being an n time function to being log n. Or we can decide to implement union by rank, which does take some more code, but I don't think it's a super complicated thing to achieve, which will also get our time complexity to be log n for find, because it will result in more balanced trees. The height of the trees will be smaller. But if we implement both path compression and union find, we get a pretty complicated math function, which is written like this, and it's called the inverse Ackermann function. You won't really have to memorize this. I don't think it's super important, but what I'm trying to get at is if we implement path compression and find by rank, this is a function, but it essentially reduces to constant time. Even for really large n values, it will usually be a constant time operation. Not literally, but it can be simplified to that in most cases. But this find function is usually not going to be run a single time. It's going to be run a bunch of times, as we were doing right now. We're trying to connect graphs together. In our example, this would be run for the number of edges that we have. Let's say that is denoted by m. So, in general, the time complexity of union find, if we have this many edges, let's say, would be big O of m times log n. But we saw if we implement path compression and union by rank, this log n can be, essentially reduced to a one-time operation. So in that case, our union find would be the time complexity of the number of edges that we had. That's why in some cases, union find can be more efficient than a DFS for cycle detection or counting the number of connected components. This can definitely be a complicated data structure for beginners, but I hope that this walkthrough did make things a bit more simple for you.